Welcome back. Um, let's try this example. With it, in this video, we will calculate the coefficient of friction for this setup. So what we have is a block placed on a rough surface inclined relative to the horizontal, like this. So we have the inclined plane, we have the horizontal, we have the angle theta, and then we're going to have whatever block we're putting here, but now this is, the surface is rough, okay? So there's going to be friction. Of course, when the angle is small, there is no motion. As we keep increasing the angle, eventually this thing is going to start falling. So let's analyze the forces acting on the block. I'm going to do a free body diagram of the block. I'm going to put the block here. I know I'm going to put, this is the surface. So of course, so first thing we have to always put is the weight. And the weight goes straight down. Another force that's acting is the normal. The normal, remember, it happens because there is contact here. And that normal force means perpendicular. So perpendicular to this surface, so that must go this way. And then because here, of course, there is 90 degrees with respect between these two, you see? Now, there is also friction. When the block tries to go down, friction is going to always try to oppose the motion. So if the block wants to go down, the friction will point up. If the block wanted to go up for some reason, the friction will go down. But here that's not the case, so the block wants to go down. So I'm going to put a friction that is going against the motion, and I'm going to say that's my friction. So what I'm going to do is I'm going to increase the angle until it's about to move. So that means if it's about to move, if 0.0001 degrees more will make this thing move, that means we are in a condition called impending motion. And at that point, the friction static is the maximum value for the static friction. So I'm going to put here static friction max. It's still not moving. So acceleration is still zero. We're still in static equilibrium. Static equilibrium. So at this point, this is the free body diagram, more or less, and we have two possibilities. One possibility is to put the x-axis like this and the y-axis vertical. However, if we do x and y like this, notice that we will have to decompose the normal in x and y, and that we have to decompose the friction in x and y, and because the weight is already in y, we don't have to do anything. So that means decomposing two forces. Well, an alternative to this is to rotate the x and y axis. This is the box. So what I'm going to do is I'm going to rotate the x and y. So x is parallel. Oh, I see what happened. X is parallel to the plane, right? To the inclined plane. And by doing this, notice that instead of having to decompose friction and the normal, now we only have to decompose the weight. And that can be, so I will decompose this force that is vertical, but now I'm going to make them, I'm going to use one force. I want it red. I'm going to decompose in one force parallel to y, like this, and this is going to be my weight in the y-axis, and I'm going to use a force parallel to x, which is here. This is going to be my weight in the x-axis. This is 90 degrees. I don't need this vector anymore. I have these two. And now a very important skill is that we have to find where the theta we have here lives in this triangle. And the angle actually lives here, right? How do I know that? Well, I want to use another color. Let's use purple or something. Notice that this line, the red one, is perpendicular to the plane. Okay. Also notice that this line is perpendicular to this one, to the horizontal here, right? So if I rotate this horizontal line 90 degrees, I get the vertical. If I rotate the dashed line, green line, 90 degrees, I get the red one. So if somehow I manage to rotate both the purple and the green 90 degrees, I'm going to get the red plus this one. So you see, that angle lives here. And that means my weight in y is mg cosine of theta, and the weight in x is mg sine of theta. So now I can add all the forces, because this is the complete free body diagram. So let's use another color. Sum of forces in x. We'll notice that x is the plane, the inclined plane. So in the inclined plane, right now, because it's a static equilibrium, there is no acceleration. In the vertical plane, the new vertical plane, the tilted plane, still the y, in the y-axis, there is no acceleration either. This block is not sinking into the plane, inclined plane, or floating, so no acceleration anywhere, static equilibrium. So sum of forces in x. What forces do we have in x? Well, I have positive mgx, which is mg, so let's do this, mg sine of theta, positive, you see the arrow is in the positive x-axis I defined earlier, minus the friction, which is the maximum static friction. And these two together, they must be equal to 0, because we're in a static equilibrium, right? Now let's do the other one here, sum of forces in y. Well, the y, the inclined y, we have normal going up, which is positive, minus mgy, which is mg cosine of theta. And these two together, they also must be equal to 0. Good. So let's call this equation 1. Let's call this equation 2. From equation 1, we can write that the friction maximum is mg sine of theta. And from equation 2, we can write that the normal is mg cosine of theta. But we have an equation 3 as well that tells us that the static friction maximum is equal to the normal times the coefficient. Remember that the actual equation goes like this. Friction static in general is less or equal to this. But if we're talking about the maximum value, then we are at the maximum value, at the limit of this equation. So the friction, so in this equation, notice how instead of friction maximum, I can write mg sine of theta, so replaces this, is equal to the coefficient times the normal, but the normal is mg cosine of theta. So that means that my coefficient is mg sine theta over mg cosine of theta. So mg cancels, and the coefficient is equal to the tangent of the angle. So in this experiment, all you have to do is measure the angle at which you have impending motion, and that gives you your static coefficient. which is just a number with no units, is the tangent of a theta, is a ratio. So let's say hypothetically that the angle is 47 degrees. So the coefficient for that experiment, including a pair of two materials, will be 1.07, which will be an extremely high coefficient. It's not easily found this in nature. Usually, as I told you before, I've made up this number, but it doesn't matter. Usually the angles are way smaller. Something for this will be like special rubber developed for Formula One or something like that. But anyways, the point is, I mean, I made up this angle, but experimentally, that's how they defined the coefficients. I showed you in the other video, like these coefficients, right? So that's the end of this video. In the next video, we will already start talking about the next chapter.